Hi everybody, back to our digital systems, our series 2. From the lecture series 1, I talk about how to use um, the AND gate, the NAND gate, or the NAND hardware as the AND gate and OR gate, and also introduced the high true or HT and low true or HT, either for inputs or output. Now for this one, we left behind with the inverter, right? Because we are going to use inverter to balance the logic wire, because you know that for the wire, that's the conducting current, right, or signals. It's supposed to be the same voltage in the term of hardware, but for some problems that let's see, if I put this one as the slash, that's gonna convert input A to be a prime, and that doesn't make sense because this one this one is 5 volt and that's turn out to be 0 volt. But sorry, for the conducting wire, the voltage is supposed to be the same throughout the wire, so that's why we're going to introduce the inverter. That's the main point of introducing inverter. For the inverter, again, the reason we call the voltage inverter because it does nothing about the logic. It just by itself. It doesn't do anything about the logic, but we put the symbol like this. That means for the input high or 5 volt or 1, you expect output to be 0 or low. And for the logic, when you have our input A high true and your output going to be your input A low true, because it's going to be opposite way, high to be low, low to be high. And for high to low, you put the half arrow at the output, but for low to high, you put the half arrow at the input. This is the symbol, and that's the agreement. This is the mixed logic symbols for inverter, and this is the alternate form of inverters. So again, the reason to add the inverter to your circuit is that to balance any given line segment. To make sense, that means in the term of supposed to have the same voltage throughout the line or the wire. Now take a look at the more example of voltage inverters. Implement voltage inverter using NAND or NOR hardware and former Boolean identities. We know that A and A gives you A. A and 1 or high gives you A. A or A give you A, and A or 0 give you A. They all give you zeros. I'm sorry, A. Now let's start with A and A. That gives you A. For your input, this is the high true. And your output, also high true. Sorry, actually this one is wrong, my mistake. For inverter, you know that you want to convert from 0 to be 1, from 1 to be 0, or low to high, high to low. And for your output here, this is supposed to be your A low true, LT, right? Simply this one is A high true. So for your low true, that's going to be your inverse. So 0 become 1, 1 becomes 0. This is the voltage inverters. And this is your symbol. You probably short your two inputs NAND gate, sorry, together. And your output going to be your A low true. A and 1, your output also become A low true. This is your symbol. And that's you use the NAND gate to implement our voltage inverters. Now for the NOR gate hardware, A or A gives you A, so your output still become A low true, and this is your symbol for your by using a NOR gate. And A or 0, that gives you A, and your output are also A low true. Okay. To make you get more clear, let's take a look at example 4.4. Use of inverters. Now we're going to introduce inverter in your circuit to balance the light segment, in the term of voltage. Suppose that it is desired to implement the logic function f equal to a prime bc or bcd prime, where the variables a, b, c, d, and d are all variables in high true form only, and if f is to be high true. NAND hardware, as described earlier in section 4.3, is to be used. So we're going to use only the NAND gate hardware. Okay, we're starting by your required to AND gate and also one OR gate. But keep in mind that they are required NAND hardware to do the AND gate and the OR gate. Next, since you need a prime, so you put the slash here. This means you are a high true. For this one, it's going to be what? A low true, right? That's how the slash work. B and C is still the same, so this is your three input are NAND gate. And BCD prime, so that's why you put the slash here, complement of BCD. And finally you OR them together. That's why you have the OR gate right here, and your outputs to become high true. Okay, that's the first step. For the second step, insert half arrows at inputs and or outputs appropriate to selected hardware. Recall that there is the implicit half arrow associated with each slash. Okay, I also put a number, the steps that I worked through. So number one, why I add half arrow? Because the slash always come along with half arrow, so you need to put a half arrow in there, same as at this point. So that becomes step number two. What about step number three? Why I add half arrow? Because I want you are required to use the NAND hardware as AND. So we worked out on this before. For NAND as AND gate, you need to put the half arrow at the output. Okay, same as step number four. What about step number five? You also add half arrow because you want NAND as OR. Same. Okay, you go back to my lecture digital system series 1. Now step number 3. Identify the need for voltage inverter. See, finally it's come to the voltage inverter to balance the light segment in your circuit, because the voltage have to be the same throughout the wire. By noting half arrow imbalances on any connecting light segments, whenever there is imbalance on the light segment, you need to add voltage inverters in the line. There are two such cases in this example. The first one is that the A prime inversion on the input line to G1, this is your G1, and the segment between the G3 input. Okay, this is your G3 input, and this is your G1. And the slash. These imbalance are resolved by adding voltage inverters G4. Okay, this is your G4, and G5, this is your G5, as shown in figure below. Note that as far as the final result is concerned, the half arrow associated with the slash could have been placed on either side. There would be the need for a hardware inverter in either case. In general, it is good practice to maintain the association of half arrows with their flow-through variables. Okay, let's work out on step number 3. You want to balance the light segment, right, by adding an inverter. Let's take a look at the G1. That's the NAND as the AND inverter. NAND as AND hardware. So this is your G1. You have your input. That's A prime, B, and C, right? So your A high true, when it goes to the slash and the half arrow, does turn out to be A prime low true, right? Because the slash do the prime work, and L is actually from the half arrow. So this is the imbalance because you have high and low. So by adding a voltage inverter, you can see that from A prime low, this one turned out to be A prime high, right? And since that we mentioned before that the voltage inverter do nothing about logic, so you put up your inverter still be the same as the input right here, which is the A prime H, true, high true. Okay, so finally it's balanced because you have H and H here, the same light segment as I circle on H. Same as the G2 to G3. you have a F output low true, and you have a slash and a half arrow. So that's turned out to be your F prime H rate. And since you start with the low true, you need to end up with a low true, because this is on the same line segment. So you add voltage inverter. So from high true, that's turned out to be low true. That's why circles are L as their low true. So it's still back to be the same by adding the voltage inverter. And if you notice, from high to low, your half arrow of your inverter, in the term of the symbol, it show up at your output of inverter. That's different from low to high. Your half arrow show up at the input of your voltage inverter. Just remind you. Okay, the last page. That's the last step, step number 4. Convert the big logic diagram into a wiring diagram. This is your final work. Simply by remove the slash marks, since they are represent logic operation only. Okay, because now we're going to do the real circuits. We're talking about the real hardware. This one is not hardware elements. I mean the slash marks. So wherever you have the slash mark, you just remove it. You leave only the voltage inverter. So that's why you have circuit like this. Gate G1, G2, and G3. G1, G2, and G3. Actually, is the 3 input NAND gate. And you can get it from IC74HC10. That's the triple 3 input NAND chip. I will show you your data sheet later. YG4 and G5 are 2 of the 6 inverters. This is the inverter, voltage inverter. G4 and G5, you can get it from 74HC04. That's the 6 inverters. When pin numbers are added to the drawing, the circuit is ready to be wired as in figure below. Note that the G3 is a 3 input NAND gate. So this is the G3. Since your 74HC10 is the triple 3 input NAND chip, but this one you need only 2 input, right? You simply are connecting pin 9 and 10 together. So that's why you have pin 9 and 10 together to have a 2 input NAND gate. Sorry, in this case have to be OR gate. Okay, so this is your final circuit. And if you go to a data sheet of 3 input NAND gate and 2 input, and voltage inverter, you will see your pin labels. So let's see, actually I have it somewhere here. This one is the 74HC04 inverter. You can see that they have 6 of them. 6 the voltage inverter. Pin number 1 as the input, pin number 2 as the output, 3, 4, and etc. Now for 3 input, NAND gate, sorry. You can see that this is your NAND gate. You have the input, the pin 1, 2, 13, and your output is 12. That's why we have the pin label on your final circuit as the 1, 2, 13 as the input, and your output simply pin number 12. So if you look quick, this is your final circuit. Your function is what? A prime. This one do the work to convert from high to low, right? From 1 to 0, 0 to 1. And this become A prime, B, and C. And also you have OR with A, B, B, C, D, and prime. That's why you have inverter here. And this one simply is the NAND gate. And this one is also a NAND gate. As you're required to do the function of A prime, B, C, and or B, C, D prime. Okay, so that's all about how to do the circuit. And since you already understand, how this work, should not have a difficult time to go on into the next topics. Okay.